All right, welcome everyone. This session is about quantum information and computing, and we're going to have the first speaker of the session is Michael Foss-Feig, who will tell us about digital quantum magnetism at the frontier of classical simulation. Please, Mike, take it away.
All right, thank you. Yeah, it's a pleasure to be here, and I've enjoyed all the talks so far. This will be, I guess, rather a change of topic and a shift to focusing on constructing complex quantum systems from the ground up. If I don't run out of time, I'll eventually show you some data, but it will be less than you've seen so far because we have less qubits. I think I'm hoping that most people are kind of familiar with, like to some degree, with quantum computing and using quantum computers, or the goal of using quantum computers as universal quantum simulators. It's an idea that's been around for a long time. I would say, while many people credit it to Feynman, but it goes back to the work of many other people in the 80s and 90s. And then over the course of roughly the last 2 to 3 decades, this idea has been formalized to the point where people now realize you can use digital quantum computers to simulate almost any quantum system you would want to, right? People have figured out and continue to find better ways to simulate both bosons and fermions using qubits. And then even, systems of infinite degrees of freedom like quantum field theories. And with all of that being said, 40 years after these ideas emerged, I think it's fair to say that at least for digital quantum computers, the idea of using them to perform calculations about, say, quantum materials or other complex quantum systems beyond what can be done classically is still kind of a dream that has not really been accomplished. This is notwithstanding a lot of progress in what I would call analog quantum simulators, with neutral atoms or with ions, where I think one could argue somewhat convincingly that these systems can show physics that is challenging to capture with state-of-the-art classical simulation methods. If you look at what digital quantum machines have done, they have a lot more flexibility to simulate all kinds of different systems in the same, say, quantum computer. But they've mostly been restricted to relatively, proof of principle type of demonstrations where you could equally well have, seen what you saw from the quantum computer using a classical simulation. And I think this is just beginning to change, and that's really the topic of my talk. And to understand why it's taken this long, it's helpful to, the reason is actually pretty simple. And it's helpful to just take a very kind of high-level perspective, which is when you want to use a gate-based quantum computer to do something classically hard, the only chance you have is to build up a state with a very large amount of entanglement, because if it doesn't have enough entanglement, it will be classically simulable. And doing that requires applying a bunch of 2-qubit gates. That's the toolbox we have for building entanglement. And those come with noise, right? Every once in a while, you apply a gate, and that gate will fail or corrupt the qubits it acts on, as shown here. And you can roughly think of that as, a countering process that disentangles the qubits while you're trying to build up that entanglement, right? So this is a game of trying to overcome that noise or build up entanglement faster than you're losing it due to the imperfections in your computer. And I think it's fair to say that now, people have demonstrated through something called random circuit sampling. It's not important that you know exactly what this is, but maybe just think of random circuit sampling as basically a game where you try to find, a problem for which quantum computers are most likely to succeed, and you do that by writing down quantum circuits that have no apparent structure to exploit for classical simulation, and also that grow entanglement as fast as you possibly can with the architecture that you're limited to, right? So they're trying to get to classical hardness before noise sets in. And this has been done in superconducting qubits. It's been done more recently in trapped ions at Quantinuum. And I think these demonstrations are pretty convincing that this type of quantum problem, albeit a very contrived one designed for quantum computers to excel at, is something that's beyond the limits of what classical computers can do now. But we want to move towards more practical problems, things that we actually care about, and we want to do one way or another, whether or not we had a quantum computer. And you can think of the statement I just made about random circuit sampling on a plot of classical cost with entanglement being a proxy for that on the vertical axis, and the number of quantum gates you need to apply to get there on the x-axis. So random circuit sampling is a game that's designed to maximize the slope of this curve, basically. So you get there in the smallest number of quantum gates. And if you look at any structured quantum algorithm, what you inevitably find is that the amount of entanglement you impart per gate tends not to be, tailored to be maximal. And as a result, you need more gates to do things that are classically hard. And so you need, better quantum computers. And the rest of this talk will be about, maybe you could argue somewhat incremental progress, but also I think somewhat important progress moving from clear advantage of quantum computers on things like random circuit sampling towards advantage on the more structured task of simulating quantum systems. And so, I said that this is a harder task in general because the gates that you're going to apply are not going to impart maximum entanglement. And I'll get to exactly how that comes about in a second. In this context, the key difficulty that we have to overcome using a digital quantum computer to simulate, the world around us is that the world around us evolves in continuous time, right? So we have, the Schrödinger equation that's invariant under time translations. And, like all symmetries, this leads to a conservation law, in particular, the conservation of energy. And, this is something we're all very used to, but it's good to step back and appreciate that it's actually responsible for a huge amount of the physics that we come to expect in the world around us, right? If you try to understand the statistical mechanics or the thermodynamics of physical systems, essentially, what we're told and, what we come to acknowledge as true is that the world around us is basically constructed out of systems that have the local non-trivial properties they do because they try to maximize their entropy subject to the conservation laws that are imposed on them, right? That's sort of the whole idea of statistical physics. And so, for example, if you put a drop of dye into a glass of water, it will have some very complicated evolution like shown here. But if you stir it up and wait for long enough time, the only property, non-trivial property left is the color of the water that is, immediately inferable from the amount of dye that you put in at the beginning. And so the same thing holds with energy and the conservation of energy. It leads to all the non-trivial properties of systems living at finite and not infinite temperature, right? That's a direct consequence of the conservation of energy. And so if you want to study a system that conserves energy on a digital quantum computer, I mean, it's very well known how to do this. So imagine you have a bunch of, quantum magnets, so spin 1/2s, and these would map directly onto qubits. So every line here is just a qubit moving from bottom to top through time. And you want to implement some energy conserving evolution, right? Just time evolution under a time independent Hamiltonian. In general, the way you have to do this is if you only have access to, say, 2 qubit and 1 qubit gates, is you break up your Hamiltonian into a sum of terms like A and B that maybe only live on the even and odd bonds. So for people that know, this is called trotterization. And when you do that, you can now approximate this continuous unitary with a bunch of discrete gates, right? And if you make the amount of evolution imparted by each gate, so if you make the time step dt suitably small, you expect this to recover the continuous time evolution. But nevertheless, any finite time step, this is not the continuous time evolution. And moreover, the closer you want to get to the continuous time evolution, the smaller you want to make that time step, the more gates you need to apply per entanglement. And this is really why quantum simulation is hard on digital quantum computers. Now, the understanding of what happens when you're not at infinitesimal time step, but at some kind of, smallish but intermediate time step is now pretty well developed, I would say. And the basic picture you should have in mind is as follows, right? If you take the time step to be truly infinitesimal, then what you expect is the system conserves energy. And so under fairly generic arguments, any quantum system and any local observable in that quantum system will relax to, a thermal value at late times that is really just determined by the initial energy and any other conserved quantities, given to by the initial state that you put in. And if you take the time step to be too large, this already came up in the previous talk, you expect flow K heating to take over right away, right? And the system should just heat to infinite temperature, which from the perspective of a local observable, it just means that all structure will be lost immediately. So the system would look completely chaotic on short time scales. And as you turn the time step, down, so, from a large value at the top of this plot to a small value down here, what people now know generically happens is that you get something called pre-thermalization, which really just means that the system, even when the time step is finite, will thermalize for extremely long timescales. They can be exponentially long in 1 over the time step. So for all practical purposes, they can be infinite, even at moderate time steps. And this pre-thermalization is kind of the same thing as thermalization. It just happens with respect to kind of a perturbatively wrong Hamiltonian. So you don't thermalize to exactly, the thermal properties of the Hamiltonian you were simulating, but one that's just kind of dressed by some additional terms. Okay. Now, I'm going to tell you about some progress we made in being able to actually see the emergence of thermalization or pre-thermalization strictly as a consequence of energy conservation in large-scale digital quantum simulations. I'm going to do that first by a little detour to tell you a little bit about how our quantum computers work. And I should have said at the beginning, I'm happy to answer any questions. So if you want to interrupt me, please do. I think I'll keep this to just like, I don't know, enough information that hopefully if you have never heard of anything about this, it will give you some idea of what we're doing, and sufficiently little that like Guido will learn nothing at all. So we make at Quantinuum traps by printing gold electrodes on a surface. And what you see when you look at this picture, every little rectangle is an independent gold electrode that has a wire hooked up to it under the surface. And we can control the voltages on those electrodes. And by controlling them in a time-dependent manner, what we're able to do is create, potentials. So, not electrostatic, but potentials above the surface of this trap that can hold ionized atoms. And so every little dot that's shown here is meant to represent a single ytterbium ion. That's our qubit. And in this particular H2 trap, we're able to hold 56 qubits. The qubit itself is basically, it's a hyperfine ground state. So it's basically just you have a spin 1/2 nucleus and a spin 1/2 electron, and they pair off into singlet or triplet. So that's the 4 levels shown up there. And our qubit is just the SZ = 0 triplet and the singlet. And we choose those for the same reason that people have for a very long time, which is that those states are very insensitive to magnetic fields. So they have a very stable energy splitting, and that makes a very long-lived qubit. Right? Long-lived in the sense that you have sort of you can put it in some axis in the XY plane, and it will maintain its phase for a very long time. One detail that I won't really even talk about is that we also co-trap all these ions with another species, barium. That's really just so that we can, in a non-destructive way to the quantum information stored in the qubit, we can laser cool the barium, which then sympathetically cools the ytterbium. And it turns out it's important to keep the ytterbium cold. So it should always be in kind of the vibrational, energy minimum of the well that it's being stored in order to do high quality gates on it. Yeah.
So the barium's there all the time and cooling it all the time, and synthetically the eternal cold, is that?
Yeah, I mean, that's not like exactly right. For example, we don't cool it during the gates because that would cause problems, but more or less, yeah, we're cooling it all the time during a quantum circuit. Yeah. Okay, and then, glossing over all the details, we do all of our quantum operations with lasers that are skimmed over the surface of this trap. So everything like single qubit gates, 2 qubit gates, measurement and the preparation of qubit states is all done by laser operations. And for people who know, our 2 qubit gate is the Mulmer-Sorensen gate. This is kind of the workhorse of gates in essentially all trapped ion systems. And the kind of limiting, error rate for us is our 2 qubit gate error, as it is for most quantum computing platforms. And right now, the 2 qubit gate has a fidelity of about 99.9. So you can think of that as roughly, you can do 1,000 gates before on average one of them will fail. And one really nice feature of this architecture, and the reason we pursued this architecture, this was sort of, I would say the reason this architecture was put forward back in the early 2000s, is that, by virtue of the ability to move all of these ions around, we can reconfigure them in arbitrary ways and therefore do gates between arbitrary pairs of qubits in this kind of a computer. So imagine a circuit that looks like schematically was drawn at the top. So it doesn't really look like a circuit, but what that's meant to represent is a request to do gates on many different pairs of qubits arranged in some arbitrary fashion relative to how they're laid out in the trap. So while they look like they're laid out in kind of a ring on this trap, and they are, we actually can move them past each other. So if you imagine we want to do a gate, like we've just done a gate on those 2 qubits, and now we want to do a gate on ones that are separated, we can move them around and rotate them past each other so that we can now, bring the next set of qubits we want to gate into the same place and just directly gate them. And if you kind of stretch your imagination and imagine just iterating that kind of a dance on a small number of qubits to all of the qubits around this ring, we can take this initial set of qubits up here with a request for gates on arbitrary pairs. We can reconfigure them until all the ones that need to be gated are next to each other. And then we can just rotate them all through the ring past these, laser beams that are, crossed here to do gates as shown here until we've implemented all of the gates in a circuit like that. So essentially the takeaway is just that while the machine looks kind of 1D, it actually has the ability to directly implement circuits with arbitrary connectivity. Yeah. Yeah, it varies a lot from machine to machine. On what I'm showing you here, the timescale for a complete round of all gates on pairs like this in a random configuration, which is in some sense kind of the worst case timescale, is about 50 milliseconds. Yeah. Okay. To some extent, but not fully. So we have only a fixed number of places where we do the gates. In this machine right now, it's 4 places. So you could think of what's actually happening here is you have, these 4 locations, say, where you can do gates. You pair up all of your qubits the way you want them, and then you just rotate them through and do them in batches. And that's something that could be improved upon, but that's, a limitation of this machine. Okay. All right, so the quantum simulations that I'll tell you about are kind of in the simplest imaginable context. And there's a good reason we started there. So we were looking at dynamics of the transverse field Ising model on a 2-dimensional grid. And so here, we chose this model basically because we wanted to be able to see the emergence of thermal physics, and we wanted to do so in a setting that was simple and for which the thermal physics was very well understood. This model has, a phase diagram that looks like this as a function of the transverse field strength that's driving, disorder via quantum fluctuations and the temperature driving disorder via thermal fluctuations. And at sufficiently small transverse fields and temperatures, you expect the system to spontaneously break, the Ising symmetry of the Hamiltonian and order either all up or all down. And then outside that region, you expect it to be disordered. And, despite the thermal physics being very simple and well understood, there's no exact way, even numerically, to probe the dynamics of this model. So, the actual approach to equilibration from an initial out of equilibrium state is a problem that is challenging to study classically. Yeah. In more than one dimension, yeah. Yeah. And okay, so here, we do this in 2 dimensions, more or less to minimize finite size effects. We do it in 2 dimensions on a torus. The actual simulations I'll show you, so these run a 7x8 torus, and that's just because, that multiplies to 56, and that's how many qubits we have right now in this machine. But, just to go back to what I said before, the geometry is something that this quantum computer doesn't particularly care about. There's no problem in putting periodic boundary conditions on the model when implementing it on this kind of a computer. Okay. And then, just to remind you, the way we're actually going to simulate the time evolution in a quench under this model is to do trotterization. So what that means in practice is if you look at a little slice of, the qubits and blow them up as they move in time through a quantum circuit, we're applying layers of gates that are basically just, little time evolutions under the Ising interaction. That turns out this UZZ is the native gate that we can implement on this quantum computer. And you just have to do for every trotter step or every time unit DT 4 layers of these to catch all the bonds of a square lattice.
Oh.
Yeah.
If you want to do 1D, you can.
Sure, yeah.
And does it work?
I've never tried. I haven't tried on this. There's a reason we haven't tried, which is that even if you made the model not, solvable in some sense, it's very difficult. It's much more difficult the lower the dimension is, I would say, to get a machine with a fixed finite gate fidelity to outperform classical methods. So it's not the place to look for a quantum advantage necessarily. But yeah, I think in principle, it should work fine in 1 dimension or in 3 dimensions. Okay. So, the experiments we ran were, you can in some sense be viewed as a very crude attempt to map out this thermal phase diagram as it emerges through the dynamics of this energy conserving system. And so just a reminder, I said before that, we expect the system to pre-thermalize, and that just means if the time step's small enough, the dynamics will approximately reveal the thermal phase diagram that I showed you before. And, we don't have access to temperature per se, but we can control temperature in the sense of the emergent temperature in an eigenstate thermalization type sense by just controlling the energy density of the initial state that we're time evolving. And that's, super easy to do because you can just take all of the qubits, say, pointing along 0. So you initialize all the qubits to 0, and you just put on, single qubit gates that rotate those qubits to some angle, and then that parametrically controls the energy density of the initial state. So that gives us essentially a handle on the temperature axis. And now, what we expect to happen is you evolve this state with some initial energy, and over very long time scales, it will pre-thermalize to a value that corresponds to a temperature set by the initial energy. And so in that way, I mean, this is just from very small system numerics, and I think it's on a 4x4 system. You could imagine mapping out something like a phase diagram by just time evolving, different states, where you just tune the angle to affect the angle of the initial state to effectively control the temperature, and then the transverse field strength on the x-axis. And, from these numerics, you can see that if you plot, this is kind of like the Ising order parameter. It's telling you basically how prone the system is to being ordered either up or down. You can see that it's very prone to do so in what should be the ferromagnetic phase. So, this kind of thermal, behavior is emerging from the dynamics as expected. Now, if you look in a little more detail at the time traces that actually generated, like every point in this plot came from time averaging some, dynamics, they look like what's shown over here on the left. And in every panel here, I'm showing 3 different system sizes, and then each panel going from right to left is increasing the time step dt. And what you see is that for suitably small time steps and all system sizes that we can easily study classically, this system does indeed pre-thermalize. So you see the Ising order parameter saturating to a finite value when you sit in the ferromagnetic phase. If you increase the time step, you start to see that this pre-thermalization breaks down and you get immediate kind of heating to infinite temperature. Yeah. I would say, yeah, that's a good question. I mean, I think there's a lot. I actually don't know what the primary reason is. There's a bunch of potential reasons it would happen. One is that it's like pretty deeply flow K, and so there's a lot of corrections to the Hamiltonian just from finite size effects. So I'm not sure what like the primary thing driving that is. It's a little hard to answer. But yeah, it's a good question. But okay, so you increase the time step enough, and what you find is that the system may be stable and thermalized at a small system size, but you grow the system size and you just see this immediate kind of, runaway heating to a completely chaotic state. And so it's a natural question to ask, if you turn up the time step, if you turn up the system size, even at a small time step, what do you expect to happen? Do you have kind of, persistent stable behavior, or for suitably large systems, are we at time steps where we can actually still see like stable thermal behavior? And, really to answer this question, it's not a question about the thermodynamics of the Ising model. It's a question about how it emerges from dynamics. And it's a question you have to answer by doing dynamics. And so it's kind of a natural candidate to try to do something classically challenging on a quantum computer. And all the data I'll show you is basically trying to answer that question for the particular quench we're doing. A natural question to ask is where one should even look for a quantum advantage in a problem like this. And it's maybe not so immediately clear, but there's pretty simple arguments that tell you where you should look. So, we often think of quantum behavior as being, most emergent at low temperature, but since we're studying high temperature as it emerges through quenches, high temperature is in some sense actually harder to do for dynamics. And you can think of this as basically, imagine as a function of time or Trotter step, you do quenches from these 3 different initial angles where the system's thermalizing to 3 different temperatures. So if the temperature is too low, the thermal fluctuations are really being controlled by, the underlying quantum fluctuations developing in the model. And that's, another way of saying that is the thermal entropy is actually being generated by entanglement entropy. And so low temperatures corresponds to low entanglement. And you can see that on this plot, where if you plot the entanglement in units of the maximum it could be for a given system size, it saturates to low values for low temperature quenches. So that tells you right away it's probably not a good place to look for advantage, because classical methods that exploit low entanglement, like matrix product state techniques, are going to do well there, or more general tensor network techniques. There's also a problem with looking, at high temperature. Strictly speaking, that would maximize the entanglement and make something like matrix product state methods fail, as badly as possible. but also it leads to weak correlations. And there's a lot of reasons one could worry that renders the simulations easier in some sense. It also renders them harder for the quantum computer because all signals will be relatively suppressed. And so it just takes, more data to resolve the structure that you have at high temperature. And so, the optimal spot to work to do something on a quantum computer that's challenging classically is kind of in this intermediate regime where you could, for example, sit next to where this expected thermal phase transition would be and have, strong correlations, relatively large entanglement, and, still a lot of kind of non-trivial signal in the system in its thermalized state. And so, what we did in the work that I'll show you is we actually ran two quenches, one at low temperature that we use as kind of a benchmark quench because we know that classical methods will be reliable there. And then another one at higher temperature where we studied, pretty systematically how accurate we believe the results are and also, what the best classical methods were and how they compare to what can be done on a quantum computer. And so here's what you see if you do a low temperature quench. So starting at, basically the mean field ground state, so tuning this initial angle to put the system in the mean field ground state. If you look at the dynamics as a function of time, you get a plot that looks like this. There's a lot going on in this plot, but I'll try to walk you through the most relevant features. So first, ignore the data and just look at the lines. These lines are all obtained from matrix product state simulations at different bond dimensions. And just to give you an overall sense of scale, doing them up to the largest listed bond dimension, it's not an impossible calculation, but it's kind of at the limits of what's feasible. It's like a hard calculation on a state-of-the-art GPU. Now, the purple line here is basically just an extrapolation from the largest bond dimensions we could do that we believe, from studying it kind of systematically is accurate. So we think this purple curve can be viewed as essentially just numerically exact up to like sub% level relative accuracy classical simulation. Now, the blue data is just raw data coming out of a quantum computer. Every point is just a circuit of some different depth from which we've extracted this observable over, I think, like 600 shots or repetitions of the circuit for every point. And so the blue data is raw data, and it clearly disagrees with the quantum data, but we employ pretty standard error mitigation techniques. So I won't go into any of the details, but we check that if you extrapolate using error mitigation techniques up to statistical errors, we see good agreement with the classical numerics in a regime where we believe they're reliable. So this kind of builds our confidence that these error mitigation techniques are appropriate and working well. So the green is you add artificial noise. This is kind of your lever arm for trying to extrapolate out the effective noises. You have raw data with some characterized level of noise, you add a little more, and then you try to extrapolate it out. Yeah. Okay, so this kind of tells us that we believe the quantum techniques and the post-processing techniques we're applying to the data that comes out of these quantum circuits is working well. And if you go now closer to the phase transition at higher temperature, you can play the exact same game and run the same circuits. If you look at what happens with matrix product state methods, you can see that this system is sufficiently entangled and sufficiently large that they're really not controlled. You can still try to play this extrapolation game to infinite bond dimension, but you see pretty quickly it really fails to be reliable after, like roughly 6 or 8 Trotter steps. So once the system is starting to thermalize. Nevertheless, the quantum data in some sense is actually more reliable at higher temperatures for reasons I could get into if you have questions. But I think, if you just look at this plot, the fact that the purple and the blue data, with blue being raw and purple being extrapolated, are close together, it's telling you that the post-processing or mitigation techniques aren't really doing a lot of lifting and gives us additional confidence that the purple data should be, like up to statistical imprecision an accurate result. And one that can't be captured by at least the simplest tensor network techniques without going to sort of impossibly high bond dimensions. So, we also looked at a variety of other classical methods that one could try to employ to study a quench like this. I'm not going to go into any of the details here, but I'll just say, we've used a variety of 2D tensor network techniques and other kind of Heisenberg picture operator methods for trying to study the dynamics here. And in general found that there's no agreement between these different methods implemented as best as we were able to implement them with a variety of collaborators helping. So I would say, I think different people will take different things from this plot, but from my point of view, what I would take from it is that with all of these methods struggling, and some of these methods being quite heuristic, for example, these neural network quantum states, it's not really clear to what extent you'd even expect them to work well at late times. if you wanted to know whether such a method was working, I don't really see anything more reliable to compare it to on that plot than the quantum data. So I think at the very least, one could say, quantum computers, I believe, have gotten to the point where they're sufficiently accurate to be used as benchmarks or standards for other classical methods that are struggling. Okay, and just to wrap up here, I think I'm pretty much out of time. I'll show one kind of cool little video, which is, another consequence of energy conservation and the approach to thermal equilibrium is you expect to see emergent hydrodynamics in the system. And, we can also, in this video, we can take this same system and just initialize it with, a kind of stripe of higher energy density in the center, and then watch that energy, diffuse out over time. And if you take that energy density as a function of space in this kind of a system and Fourier transform it, and then you look at the way its different momentum components decay with time, you can even do things, relatively quantitative, like extract the diffusion coefficient, associated with this hydrodynamics. All again, this is all just extracted from quantum data here. So, okay, with that, I'd like to just wrap up and say thanks to many collaborators. I'll call out specifically Reza, who really kind of led the numerics effort for understanding 2D tensor network methods for this project, and Ellie Cherkov next to him, who led the actual design and implementation of the quantum circuits, and then Mike Mills, who sort of was leading the development and operation of this H2 quantum computer at the time we were doing this. Thanks very much for your attention.
We have time for a couple of questions. Yes.
What about normalization as a result of just polarization? If you quench these two models, it's another reason for normalization. Shows we have Michael as a collaborator, so something often as a postdoc, that after normalization, even if you honestly do continuum evolution, and during this time, actually, you find that the system does not satisfy coefficient dissipation theorem. And in fact, it gets much longer, exactly near the transition point, like a signature of critical slowing down. So is it clear that your plateaus are really flatterization plateaus and not this kind of intrinsic pre-formalization, the system not formalizing?
It's going to be hard for me to answer with confidence on the spot, to be honest. But I think to me, it's relatively clear because you do see that they're primarily sensitive to the Trotter. I mean, the duration of these plateaus is primarily sensitive to the Trotter step. But I don't know that that's particularly conclusive.
There is another plateau which has coefficient dissipation would not be satisfying different degrees of freedom, not having the same effect in temperature.
I mean, I guess I don't see why these two things couldn't coexist, to the extent that if this prethermal plateau is long enough, it can contain any of that physics within the Dressed Hamiltonian that it accesses. But I don't know like the order of timescales. What's that? Yeah, maybe, and it might be. Yeah, I mean, you might be able to. Doing so cleanly might require going to kind of much longer times and circuit depths than we could feasibly do right now. But maybe it would be interesting.
Yes.
I seem to remember a controversy from a few years ago where IBM did a Ising model, and they're somewhat claiming they could do tensor network simulations immediately afterwards. So is this loophole free compared to that?
I mean, I think nothing in this kind of, endeavor is loophole free. I mean, I would say, so I think we tried to be relatively careful in terms of like putting a lot of effort into understanding what state-of-the-art methods are. But like I said, there's various kind of, improvements that could be made even to, controlled methods with bounded error. There's also many heuristics, and one can't, ever rule out that it would be possible to simulate something like this. I'm more trying to make the argument that, I don't know, in the world of like claims of quantum advantage, I guess like this has lasted for a few months, which is already like, maybe more than typical. And so I think, I think that's actually saying something, though. In my mind, what it says is that these computers are tools that should be at least in the mix with classical methods when comparing, when assessing what methods are accurate.
All right, one last question.
Why unique attention from this one?
Why it would be more difficult to do on a quantum computer? Oh, I mean, for us, it really makes almost no difference. I mean, there is like a little bit of a win to doing 1D models because of the actual underlying 1D configuration of the ions. Circuits that are in 1D would run a little faster, but they wouldn't really run honestly appreciably better. And on the classical side, it's very clear that at least for tensor network methods, higher dimensionality always wins out because your entanglement, like the slope of your ballistic entanglement growth will be steeper. No, we only compared to it in the exact case in 2D, where it was also available in this lower temperature setting. But we haven't done that in 1D. At least, well, maybe we have at some point, but in this particular project, we did not do that in 1D.
Thank you, Mike, again.